Everybody, today I'm going to present another sampling-based path planning algorithm called the RRG, which stands for Rapidly Exploring Random Graph. This is presented by me, Ashraf Faraj, January 20, 2024. To remind you, this is the familiar setting that we're going to use. We are trying to find a path from this point right here, the start, to the goal right here, trying to avoid the red circles, which are the obstacles. Now, this figure here shows an example of a path that is generated by the RRG algorithm. Well, what we can see here is that we have actually abandoned using a tree and started using a graph, which gives us more kind of ability to navigate more complex paths. Now, the RRG was actually developed to address the problem of lack of optimality of the RRD algorithm. It can be shown that the RRG is actually probabilistically optimal. That is, given that the number of nodes generated tends to infinity, we are guaranteed to find the optimal path within the generated graph. And now this is actually really good news because now we're able to find optimal paths, which was not actually possible with using the normal RRT algorithm. The only problem is that this comes at a larger cost. As can be seen here, the graph is actually really complex, which really requires many edges and probably many iterations to find a possible path. I'm going to discuss the RRG algorithm in detail. First, we initialize the nodes to start and the edges to an empty list. Then we initialize the graph using the nodes and the edges. Now we repeat the following steps for the maximum number of iterations n max. First, as usual, we take a sample from the free space following a certain distribution. Now the main step here is that we're not only going to look at the nearest node, as in the classical RRT, we're going to look at the number of nodes in the graph that are within the radius of the newly generated random point. So this will give us a set of nodes from the graph that are an Euclidean distance less than or equal to radius from X rand. Okay, so now we have a set of candidate parents rather than one candidate parent in the classical RRT, which was the closest node only. Now, for each of the nodes that are in the X neighbors set, we do the usual extension process. We attempt to extend between X parent and X rand and this graph. Now, if we found that this was actually possible, then we update the graph by adding X planned to the nodes list. We should, of course, in implementation, pay attention to add X planned only once if we have ever found any edge. And we're also going to add an edge if and only if this planning process is actually possible. So we might add multiple edges here for each parent in the X neighbors set. And finally, if this X planned was actually in the goal region, we're going to save the goal index and keep the algorithm running for an n-max iterations. Finally, we're going to use the A-star search to plan a shortest path in the resulting graph using the goal index just to indicate which node we're actually desiring to reach. I'm going to show the results. So the figure on the right shows the path generated by the RRG algorithm on our kilobot example. We can see here the black edges actually are the edges of the graph. We can see that they actually well approximate the free space of the robot. We can see now the blue path being the path that was found by the search algorithm when searching on this graph. It can be seen that the path is actually nearly optimal. The optimal path actually being a straight line from here to here and then a straight line to the goal. Because as we said, the RRG can be proven to be asymptotically optimal. As the number of nodes approaches infinity, we are guaranteed to find an optimal path between the start and the goal nodes. The downside, however, is as we can see a huge complexity of the graph as compared to the traditional RRT, which was actually quite simple. Now, the problem is that this huge number of edges might actually cause numerous memory problems which makes the RRG quite undesirable. For conclusion, we presented the RRG algorithm in detail, and we then implemented and tested the RRG algorithm on a path planning problem for obstacle avoidance. Now, as we said, the RRG solved the optimality problem, but actually gained a lot of cost because we had to create a huge number of edges. Now, another algorithm that actually solved the optimality while actually trying to not increase the cost drastically is the RRT star algorithm, which merges the RRT and the idea of the star search into one algorithm. Now, this will be presented in other videos in the future. And thank you for listening. That's it for today.